Chemical equilibrium. Most chemical reactions do not go to completion. The reactants form products, but the products also form reactants. And so these chemical reactions are said to be reversible. Look at the two opposing one-step reactions. H2 plus I2 forms 2HI, and then 2HI decomposes. Instead of writing these reactions twice each time, normally what you would do is use a reversible arrow, like this, and just write that reaction once. Regardless of the amount we start with, the initial rate is very rapid. But as you use up reactants, in this case H2 and I2, the forward rate slows down, and as we produce product, the reverse rate picks up, and eventually the two rates become equal, and we are in a state of equilibrium. So this chart shows reaction rate versus time. The forward rate is up here. The forward rate proceeds very quickly at first. The reverse rate is down here. Initially, the reverse rate is 0 because there's no product, but it starts to pick up over time, and eventually those two rates become equal, and we are at a state of equilibrium. So chemical equilibrium is a state in which two opposing reactions are proceeding at the same rate. If you think back to kinetics, you have the forward rate and you have the reverse rate. At equilibrium, the two rates are equal to each other, so we can set these two rate expressions equal to each other, and we can solve for a new constant. This is the equilibrium constant K, which is a capital K. The lowercase refers back to kinetics. This chart shows data on that particular reaction, H2 plus I2, 5 different trials. You'll notice that in those 5 different trials, the initial concentrations were all different, but notice the K value, the equilibrium constant K value, pretty much identical, because the K depends on equilibrium concentrations. K does not depend on initial concentrations. So in general, for a chemical reaction, equilibrium constant is given by products raised to their powers divided by reactants raised to their powers. So if we look at this reaction, N2 plus 3H2 forms 2NH3, K would be equal to products, which is NH3, and we're going to square it because of the coefficient, divided by N2 times H2 raised to the third. So even though this is a reversible reaction, products are on the right side of the arrow. Let's look at a few examples solving for the equilibrium constant K. Now in this one, it says solve for Kc, which stands for concentration. We're going to write the expression first. Products, which is BrCl, it's going to be squared because the coefficient, divided by reactants, Br2 times Cl2. So there's my expression for K. I want to get the numerical value. When you're solving for K, you have to make sure you're using equilibrium concentrations, and we are. It says at equilibrium the concentrations are as follows. So we plug in the concentrations. So 0.02 squared divided by Br2 is 0.1, and Cl2 is 0.09. Now K is a unitless quantity, so even if the concentrations did not cancel out, K would have no units. So here is the value for K, or Kc, since we're using concentration. In this next example, we're given the balanced equation, and we're given the initial amount of PCl5. But what I need to do first, before I solve, since I'm given grams, I need to change that to concentration. So we're going to take 35.7 grams. We're going to get the molar mass of PCl5, which is 208. And we're going to divide by the volume to get molarity, 5 liters. So the concentration present initially is now in molarity. We're going to do the same thing for Cl2. This is at equilibrium. and we're told that we have 8.75 grams. Molar mass of Cl2 is 71. So that'll give me moles divided by liters, 5 liters. So at equilibrium, there's the concentration. So that's the two pieces of data that we are given for this problem. I'm going to move to the next slide. Write my balanced equation. And we're going to set up something that I call ICEBOX, which stands for initial, change, and equilibrium. Okay, so plug in what we know. PCl5 initially 0.0343 molar, and equilibrium Cl2 0.0247 molar. That's all we know. Now initially, the products would be 0. So I know the change for Cl2 is 0.0247, and if I know the change for Cl2, because the coefficients are 1 to 1 to 1, I know the change for everything else. So this is the important line right here, the change. The change for PCl3 would also be 0.0247, so at equilibrium, that's what I have. The change for PCl5 would also be 0.0247. The only difference is this is going to be negative because it's a reactant. So we have to subtract to get the equilibrium concentration of the reactant, 0.0096. So the change, this line right here, is the important part, and you look at the coefficients from the balanced chemical equation. All right, once we know the equilibrium concentrations, we can solve for K. K is products divided by reactants. So we're going to do products, 0.0247 times 0.0247. And there's no coefficients here, so we don't have to square or cube or anything like that. Then divided by 0.0096. And again, K is a unitless quantity. So K comes out to 0.064. Okay, we have a balanced chemical equation. Again, we're given the K value, 0.025. We're given the initial concentration of SbCl5. So I'm going to start with the equation. We'll do an ICEBOX, initial change equilibrium again. The only thing I know is the initial concentration of SbCl5, which is 0.1 molar. I do know the products would be 0 though. Okay, I know the K value, but I don't know any other piece of information to go in the ICEBOX. So I'm going to use x's. So I'll say the change here is minus x, and the coefficients are all 1, 1, 1. So if the change is minus x here, on the product side it'd be plus x, because I don't know the equilibrium concentrations of anything. Okay, so there's my ICEBOX set up. And I know that K, which is 0.025, is equal to products at equilibrium, that's x times x, divided by reactants, which is 0.1 minus x. And we can simplify this. So we can do 0.025 multiplied by 0.1 minus x equals x squared. And we can simplify this even further. X squared plus 0.025x minus 0.0025 equals 0. And this looks like the quadratic. So we're going to use the quadratic in order to solve for x. So I'm going to move to the next slide. The quadratic is x equals negative b plus or minus square root of b squared minus 4ac over 2a. And in my case, a was 1, because it was just x squared. B was 0.025, and C was negative 0.0025. So you can plug in those numbers and solve for X. You're going to get two answers, but only one is going to work for us. So I'll assume you know how to do the quadratic and plug those numbers in, but you're only going to get one answer that works. X comes out to 0.039. So that is going to tell me the concentration of SbCl3 as well as Cl2. Those are the equilibrium concentrations, 0.039 molar. I can get the concentration of SbCl5 because at equilibrium it's 0.1 minus X, so 0.1 minus 0.039. So at equilibrium, SbCl5 is 0.0610 molar. And those are the two numbers that I needed to solve for as far as the equilibrium concentrations of all products and reactants.